very brief and crisp. In order to provide global exposure to our students, we have been organizing a lot of programs, inviting learned professors and industry experts from various countries. So today we have with us Professor Richard M.Voyles from Purdue University, which is one of the leading, popular, high-rated universities in the USA. So he is going to talk about robotics, in particular Dr. M.Voyles, our principal madam, and the heads of departments, faculty members, and also Professor Richard is an authority in robotics, inspiring, interesting, and motivating also. So with this, let us move further, and I hand over to the MOC team. Thank you.
So today is going to be a very interactive session for all of you. And it's a good opportunity for all of you to have Dr. Richard M.Voyles with us. So he is from a reputed university, Purdue University, which is in one of the top 10 universities in US. And he has done his undergraduation in Purdue University itself in electrical engineering, and MS in mechanical engineering in Stanford University, and Ph.D. in Carnegie University in computer science and robotics. So you can see that this graduation is all in reputed universities with a mix of disciplines: electrical engineering, mechanical engineering, and computer science engineering. And that is why today he is heading the Collaborative Robotics Lab in Purdue University. And he has also worked at White House. So he has got an opportunity to work in all government, industry, and also in academia. And he has got very rich experience. And his experience is double than your age. So today you are having the gifted opportunity to listen to him about robotics and how it is going to rule the world. Today if you see, robotics is there in every field of engineering. It's in healthcare. If you see now they're using it for surgeries and all for domestic purpose, and many applications it is being used. And now Robo is not a single discipline engineering product. It is being created by a group of engineers of different branches. So we always insist that you should have multidisciplinary knowledge. You should have knowledge about every branch of engineering. Only then you can come up with a product which will be relevant to this world, right? So all your products which you are using is mix of all engineering. Like your car and other items, if you take your mobile, you have all the branch of engineering which is being incorporated in that. And now he's the right example for you to understand that today the world is moving toward multidisciplinary education. And so take that point in your mind and see that from first year onwards, you have some, you learn some courses on other branch of engineering apart from your branch of engineering. And today you can hear from him, and this rich knowledge will be definitely useful for all of you. Thank you.
From the introduction, it sounds like I'm a pretty old guy who's been around for a long time. And I am, but at the same time, I love what I do. It keeps me young, at least young at heart. And I hope the same for you as you start in your new journey on your way to becoming an engineer and maybe a Ph.D. as well, and faculty member. You know, that's a lot of information. But I'm going to talk about this from the standpoint of what makes robots really the most different from every other form of AI and engineering, and that is the connection to the physical world. And that's what happens with motion or actuation. And I'm going to talk about locomotion, right? The ability of robots to move around and how that is getting more and more complex, which requires, much more out of the silo or out of the box thinking that a traditional individual branch of engineering doesn't really cover fully. And so, get this in here later. And so I mentioned Robotics 3.0. mean when I say robotics 2.0 and robotics 1.0 and these different numbers, many of which you probably haven't heard of. You're thinking, well, gee, I'm kind of interested in robots. Maybe some of you are. Maybe some of you aren't. Who here is actually interested in studying robots as part of your program? Yeah, see? There's a good number, but not everybody. We'll convert the rest of you later. But what we started, and this was really an international effort to redefine what was just robotics, and to make this distinction of now, collaborative robotics is what we're calling now robotics 2.0. And it's really about the synergistic interaction between robots and humans. And the problem with that is, well, if we're talking about robotics 2.0 already, well, what was robotics 1.0? My definition that kind of captures really what robotics 1.0 was all about. Yeah, it has to do with these dull, dirty, dangerous tasks, unfortunately done by dull, dirty, and dangerous robots. But really, I think the problem with robotics in the 70s, the 80s, the 90s, and into the early 2000s was for a long time we talked about lights out factories. Well, how many humans are going to be in a dark factory? 0, right? That was the whole idea between the way we sold robotics in the 70s and the 80s in particular was we're going to have lights out factories, they're going to operate autonomously, occasionally a maintenance person is going to squirt some oil or charge some batteries or whatever. And it took humans out of the picture. Because humans were kind of viewed as, well, what are humans? And those are all the things that robots do well. But humans, right, if you compare ourselves to a bear or to a lion, right, or even an elephant, right, all those things have clear physical strengths. They either have big teeth or big claws or really thick skin, or they're just big, right? Humans, what do we have? We have no arm, okay? You don't have sharp teeth, you don't have claws. Exactly. Yeah, we think. We can solve problems, and we can solve problems in real time. That's what robots, to achieve a lights out factory, you need. And everyone kind of forgot that. And that's why there's a problem. And this whole idea of robotics 2.0 is that, we actually have to break from that history of thinking humans don't belong in the picture of manufacturing, for example, and certainly for other types of robotic uses like home health care, right? Or self-driving cars, where the cars interact more with other people and other drivers than they do with other robots, right? And so that's what we meant by robotics 1.0. Because, to be honest, we tried this for about 30 years, and it really didn't work very well. What a play about robots it was about. Evil robots, right? That's the story of a lot of science fiction. And if you look at these, now these are not evil robots. Sorry, I'm an old guy, remember. Some of these are too early that you don't even recognize. But many of you recognize at least some of these robots up here, I hope. This is Rosie the robot. She was a maid from the 1960s science fiction cartoon. Of course, Star Wars, yeah, anyone know what C-3PO's actual job was? What was C-3PO? Anybody know? Any Star Wars fans? He was called a protocol droid. Okay, that means his only job was to interact between humans. Sounds like a collaborative robot, doesn't it? A maid robot. Maid robot, right? Cleans up, but cooks for the family, right? Organized the family, got them all together, got George Jetson out to work, got the kids off to school, right? That was a collaborative robot. Even this guy from the 1950s, he was on a spaceship, and he helped Buck Rogers, get to the moon or wherever. And all these robots, R2-D2, also, these are all examples of collaborative robots. So, in science fiction, we really skipped over the whole Robotics 1.0 and have really created this false image. Use of the word robot was a dystopian view of the world where the robots revolted against their human creators and killed them. First ever use of the word robot, right? We have to, as engineers and scientists, we have to deal with that history. It's interesting and fun, but potentially troublesome. So with that in mind, the problem again for us is how do we explain to a public that is used to those and doesn't understand these very much at all, and then convince them, oh, by the way, yeah, these things can't make our dinner, they can't give us they can't even, things that we call common sense, they're not capable of doing. But this is the realm of, I talked about unconventional locomotion. I'm going to talk not about Robotics 2.0, Robotics 1.0, or Robotics 0.1, but remember, I want to talk a little bit about a little bite-sized chunk of just robots that move around, okay? Now, it turns out every one of these robots here is teleoperated. And that means it operates at a distance, which means there's a human pressing the buttons. So by definition, they too are collaborative robots. They can't function without their humans. And their humans can't function without them. Okay? And these are all examples of emergency response robots. And what I'm going to focus on is not their intelligence, because they're not very smart. I'm not going to talk about their sensors, because those are primarily used by the humans, not by the robot. Okay? Instead, I'm going to talk about the locomotion. The legs, the wheels, the treads, the things that make the robot move. Okay? Now, I should define first, I talked about Robotics 2.0, I talked about Robotics 1.0. I even talked about science fiction, Robotics 0.1, but I haven't actually defined a robot. There's a lot of disagreement on what's a good definition for a robot. Now, limbed robots are really a complete different sort of animal, if you will, and they are based on biological creatures, on animals. There are really two classes: human-like, which are dynamically balanced. Right? I don't fall over. Now, if I were to fall asleep, I would fall over. If I were to anesthetize my limbs, I would fall over, because they're actively controlled, right? I'm controlling my balance by constantly moving my actuators. Remember those actuators? Right? And I have to keep doing that, or I will fall over. About several centimeters. Here's some kind of spider-like devices here, but these are, these legs that just happen to be designed with spikes so that they can crawl up wood and things like that, much like an insect, which also often have spines in their legs. You're just giving it traction. But they're fundamentally, and this is an example, it has 6 legs altogether. I'm sorry, this one has 8, because there's a couple versions of this robot. But the bottom line is, these are all different forms of, those legged robots I'm referring to also as conventional locomotion. Okay? However, this is one of my robots, and this is a form of limbed robot, but it's a little bit different than most of the others. All of those other examples, including myself, right, the legs are entirely supporting the body. But it turns out that in the biological world, while it's not uncommon, it's more common that the environment supports the body. Fish, for example, right? Fish just kind of swim there. Crabs, they may have legs to help them walk, but they're basically buoyant, so the water is holding up the most of the body. Alligators, right? They just lay on the ground, and they actually drag their stomachs along the ground as they're walking most of the time. Now, alligators can lift the entire body up when they want to run really fast for short distances. But most of the time, they're supported, their mass, supported by the environment. So these are very efficient. We have to carry our weight everywhere, okay? And that takes energy. That reduces our efficiency. My robot here, initially I said, well, I'm going to use that approach. And instead of, it's a biped, but it's too energy expensive to actually have it stand up and balance itself and carry all that weight. So I said, well, I'm just going to make it drag itself on the ground. Okay? So the mass lays on the ground, and then the limbs actually just pull it along. Again, this is used for emergency response as well. And so a quick video here. Hopefully, not starting. Oh, click on that. Not getting video hasn't started, but that's okay. I'll skip over it if you let's click on that maybe. Just see it start up. No, that's okay. I'll go to the next one. This is another form of limb robot, but it's unconventional as well. So while dragging the body, supporting the body by the environment is conventional in biology, it's not so conventional in engineer design. And sorry I can't do it, but that's all right. And then of course snakes. I'm going to skip over the snakes. There's a whole body of research on snake locomotion because there's so many. Oh man, I can't show you these videos either. This is a snake robot. This is a glass tube. It can actually crawl up the glass tube simply by pressing opposite parts of its body out against the tube, and then it kind of wiggles around. This is a version of a sidewinder. Unfortunately, this is a real interesting robot. This is an unconventional form because what's happening here is this robot has a skin that's actually toroidal. So the skin folds in on itself. And you can see that the skin is like a giant cylindrical thread. The whole skin is moving on the robot, folded inside, and it has an articulation to allow it to go through. And then see the skin pulling through, right through. And you know, we talked about this vehicle, which is a commercial version. This is another kind of combination of treads and hybrid, treads and limbs, and that's what the rest of these are. But the unique features of these two, like that robot that snuck through the fence, these have full coverage of the treads. So you can see the treads move around here. They also move around here on all four sides. So if the robot falls over, it still has treads on the ground. Okay? Same is true of this one. And then they have actuators in between that allow them to steer. So they can turn to the left, they can turn to the right, they can go upstairs, and different things like that. I already showed you this with toroidal drives, are very similar. This is something with a circular cross-section. So it looks like a sausage, but it's actually a robot. And these two threads are actually full cylinders. But you need two of them to purposefully go anywhere. Okay, but the advantage of these threads is there's never a place where the robot can get stuck, where it doesn't have a foot on the ground, if you will, because the entire surface is covered with the threads. And that full body coverage is this problem, what we call getting high centered with locomotion. That if you have treads around individual threads around the cylinder, if you have a rock or something that gets in here, it'll lift both of these threads off the ground, and then the threads don't work anymore. They'll just spin in the air. Okay? And that's a problem with many of those mechanisms that were designed to combine the tread function with these joints like a limb function. They can still kind of get stuck. And that's one thing that we were looking at from a mechanism standpoint, is, okay, how do you take the basic limbs of our crawling robot and then add a tread to give an unconventional form of what we call heterogeneous differential drive. So now you've got, on one side, you've got limbs crawling around, and on the other side, you have a tread. Now we don't see those very often because, like wheels, we don't see treads in biology. But it turns out we do see a lot of heterogeneous drive structures in biology. A grasshopper is an example, right? A grasshopper has some little tiny legs in the front and big giant legs in the back, right? And the big giant legs are for explosive locomotion. It can make huge jumps and escape a predator quickly. Whereas the small front legs allow it to crawl and eat, things the size of its mouth, okay? Much smaller than a predator. And we see that a lot, these heterogeneous locomotion structures. So I'm going to skip over this in the interest of time. But I am interested in that. I hope this one runs. In biology, we see those heterogeneous actuation structures. Okay, so over time, we're seeing this complication exist, where we started with wheels. That was easy for engineers to design, or to build and design, but it doesn't work in the natural world. You need to build a road for it to work. So as soon as you get in the natural world, we start to have problems. So we added treads. That was a form of hybridization. You're carrying your road along with you. Can't get up the steps. By adding a simple limb to treads, now we can do things like climb up steps. And in fact, that robot is can climb over obstacles like rocks, but also up steps, into holes, different things like that. There was some attempt to what if we just add more and more of these treads? And yeah, it could do a little bit more irregularity, but didn't add a great deal of capability compared to the level of complication or complexity that all these motors and actuators add. And control. The humans trying to control these things that are teleoperated don't work very well. And then stuff like this, well then that brought additional problems. And that's where we were looking at, along with some of these other researchers, this type of robot, which is now a combination of not just kind of a bimodal hybrid, but trimodal, where we're now combining treads here with limbs in a serpentine or snake-like configuration that allows us to get adapt to all kinds of rough terrain, including things like crevasses, where you kind of have to build bridges to get across. Again, certain constraints, obviously, but we see a lot of this kind of adaptability in biological structures as well. But again, it's a growing level of complexity that is coming from hybridization of different modes, of different simple basic modes of locomotion. Now, I want to point out one quick thing, that there are two real branches of robotics. There's moving around, mobile robots, that's the locomotion part. But then there's also picking things up, right? That's manipulation. And there's an interesting duality between locomotion, if we have a robot crawling around on the earth, is really a lot like manipulation, okay? When you have a multi-fingered hand holding, say, a ball, you know, a robot crawling around on the outside of the ball is really a lot like a hand manipulating the ball. And so there is this duality between manipulation and locomotion. And then again, this increase in performance as a function of hybridization. So I'm going to say just one quick thing about how we fabricate these things, which now requires, because of this level of complexity, the design problems of adding hybridization, more and more complex combinations of actuation, I think is really moving to the point in my lab where we need to have, I should also point out that, you know, the silos that we've developed in engineering, electrical engineering, mechanical engineering, computer science, computer engineering, are starting to merge. We need, with these increased levels of complexity, we need more sensors for these mechanisms, these actuation mechanisms. We need mechanical design. We need electrical design. We need software and computer design, all simultaneously, but we still tend to do these things separately. And then we get communication problems. I'm interested in the area of co-design, where we're doing all these things simultaneously, but we don't have good ways of fabrication. And that's where fabrication comes in when I talked about novel forms of locomotion, but also the ways to build them. We need to start, and 3D printing, I think, is a great way to abstract the complexities of fabrication so you can just press plant. Nobody has to know how to use a lathe anymore, or a mill, or, you know, many of those complex machines for subtractive fabrication with the 3D printing. Still need to know about materials, of course. But that doesn't help much with the computer, or the sensor, or the other elements of that design. And so what we're looking at is holistic fabrication of sensing, computation, and actuation simultaneously with form, which those functionalities combined with form, or typical CAD models, we call form plus function 4D printing. And so we've been developing this on a 2-degree plane. So these are folded robots. In this case, it doesn't have a printed actuator. It has printed sensors, printed computation, and printed structure. But you might ask, well, wait a minute, where's the printed computing and the printed software coming in? And that's one of the areas that we're really starting to put a lot of effort into polymer electronics and neuromorphic architectures. So basically, artificial neural networks can be printed on surfaces. It does the automatic planning of those, with structure, so that you can add the sensors, computation, and actuators to the form and shape of the object that you're designing. And that, I think, is really going to enable what I call Robotics 3.0, where we have smart materials that are really one and designed with the function of your robot or other smart device. So I think I'm going to, since I've gone over, I'm going to call it there, and thank you for your attention. I think we might have a few.
Yes. First of all, I'd like to thank our chief guest, Mr. Richard, sir, for his presence in our institution. I don't know how many of you are aware of that. Purdue University is one of the top 10 private universities in the US. It is really our pleasure and honor to have you in our session, sir. And to be very frank with you, as we have mobile in hands, no doubt that for 10 to 15 years to come, or at least 10 years to come, we will have every robo in our day-to-day life. Okay? Sir, in the short span of time, just covered what robotics, the type of robotics and type of locomotions, and that to apply to even talk about the manufacturing, mechanism of manufacturing the robot and how we can apply for day-to-day life as well as in neuroscience. If you clearly watch, he has started from the scratch to the latest applications. I'm sure we are going to see to us, sir. Probably, maybe in 1 or 2 years, probably we will have a department of robotics in our institution, and we will call it a GPS department. Thank you so much, and I thank all the deans as well as the head of the departments for making your presence here and gracing the occasion. And last but not the least, my student volunteers